Here come the men in black. Okay, so we're looking at thin lenses right now. And we call them thin lenses because, generally speaking, they're thin. Like if you're looking at this lens here, it's not that thick. It kind of fits like a little wafer in between your fingers. The real reason we're using thin lenses, and we'll see this coming up shortly, is that if we have a very thick lens, okay, something like that, what the lens is actually doing is it's bending light, and what we are trying to assume is that wherever this light ray is bent, it's going to come out in like the same spot on the other side. So we're like pretending that it's going to come out up here. What's actually happening is this ray is going to bend, and then it's going to bend again. Now this is like super exaggerated here on the bending, but like what I'm trying to show here is that the difference in height, this right here, that causes issues. Like that is literally a issue in ray optics with lenses, that the lens has some thickness to it. So we are going to pretend that our lenses are like very, very thin and we just don't care about it. Technically, if you are trying to show what happens to a ray inside of a lens, yes, it is bending and then bending again when it leaves. And we'll talk about why that is in a later video. But for right now, we're just going to assume that these lenses are very, very thin and that they cause the light rays to bend. Okay? Now, when we talk about lenses, we have two types of lenses that are interesting. The first is a concave or a convex lens. A convex lens is bubbling out on both sides. Okay, it's actually the lens I'm holding in my fingers right here. You don't have this in your hand, but if you're holding a convex lens, you can actually feel how it like bubbles coming out like that. Okay, and it's a convex lens in a similar way that a convex mirror, is shaped like this, right? So we have a convex lens, and technically this is a double convex lens because it's convex on both sides. You can have things like convex plano, where it's a plane on one side, or a convex concave, where it's vex on one side and cave on the other. You do all sorts of interesting things with lenses. As we talked about with mirrors, like you could draw some like wavy thing in order to reduce spherical aberrations. But we're probably going to just sit with double convex, which we see here, or a double concave like this. So this is a convex lens, and this is a concave lens. Now, we'll commonly call convex lenses, we'll call these converging lenses. And our concaves, we're going to call these diverging lenses. And there's a specific reason to that, and we'll see exactly why whenever we start looking at some of these ray diagrams on the sheet here. So if we look at these ray diagrams, let's first look at a double convex lens. Well, what's going to happen is, if our object's out here, here's the arrow, what's going to occur is a ray of light, we can draw some rays again. Our first ray that we can draw is just a flat ray that's going to strike the lens. And just like for mirrors, when we had a concave mirror, our first ray struck the lens, and when it reflected out, it went past through the focal point. That's the same thing that's going to happen here. Our light ray is going to bend at this time through the lens, and as it bends, it's going to pass through the focal point, okay? Right there. So first light strikes flat, and then it goes through the focal point. The second ray that we can draw, and really you only need two rays to do this, the second way we can draw is to go exactly through the center of the lens. If you go exactly through the center of the lens, you should not see any deflection of the light. The light won't bend at all. So you can draw a perfectly straight line. With just those two lines right there, we have a connection. We have these lines converging at a point, which means that this is our image. If you also wanted to, you could draw a third line. You would go through the focus on the left side, and then you'd come out straight and flat on the bottom. This is just the mirror, or the similar image to the orange line from above. And this is because for a double convex lens, there is a focus on both sides, because light could come in from this way, or it could come in from the other way. Okay? Either way, we're going to focus it. So those are the 3 lines that we can draw. And because of this, we can generate a real image. Notice here that our object is, pointing up. Our image here is pointing down. We've inverted, we've flipped, we created a real image. Because of this, we'll actually see that everything we learned about a concave spherical mirror is the exact same as a double convex lens. There are 6 different cases. If your light's at infinity, you see the light coming in and then all passing into the focus. If your object is outside of twice the focal length, which remember this is the center of curvature, we see an image created between the focus of the focal point and the center of curvature. Note it's smaller. As we bring the object into the center of curvature, we see an image at the center of curvature on the other side. On a mirror, this is when we saw it as, the image just popped up right here, the exact same. When we're inside, between the center of curvature and the focus, we see that we get magnification. This is actually a magnifying lens here. When you're at the focus, we see that the way our light travels through, these rays are parallel and you don't get an image, so there's no image here. Exactly the same as what we saw for a mirror. And when we're inside the focal point, our lines actually diverge, and then we get an imaginary image on the backside. I think I misspoke. Case 4 isn't a true magnifying glass. We are getting a magnification of an image here, but it's upside down, which will be annoying if you're trying to read. A true magnifying glass will give you an upright image. It's virtual. This, case 6, is a magnifying glass. Sorry about that, I misspoke. But it's the exact same thing that happened with a concave spherical mirror. They're the exact same. If we take a look at a double concave lens, well, it's going to act the exact same as a convex mirror. For a convex mirror, what we saw is when the light struck the mirror, it reflected out, and all of the light rays ended up diverging and never reaching one another. And we had to backtrack through it in order to get virtual images on the backside. We're going to get the same thing to happen here, but in a slightly different way. What's going to occur for these double concave lenses is that your light ray is going to strike the lens, and it's going to deflect away from the focus, like this. It turns out, though, if you backtrack this light, so let's backtrack this light real quick. If we backtrack the light, it will pass through the original side's focal point, right here. The second line we draw is the same that we drew for our double convex lens. You just go through the center of whatever lens you have, and you're good. Now we see that these points have matched up, they've crossed somewhere, and that is where our image is, right here. This is weird because the light isn't actually here. Like, the light is not actually intersecting at this point. The light went over and then it went out. You've got a bunch of rays that are diverging over here. They're really doing this. But what your eye sees, because your eye is still back here looking through the lens, your eye sees the image form right here. Except this is an upright image, which means that it is virtual. And because of that, these double concave lens, where if you're holding one, you can actually feel the drop in it, they'll always create for you upright images. See how small my head is right there in that lens? That's because this image will always be smaller, just like for our convex mirror, it created smaller images as well. Compare that to the double convex lens, which is like a concave mirror, where, oh, look at that zoom. Look at that zoom. Look at that zoom. Look at that zoom. You get some serious zoom there. At some point, you kind of get a flip out of that. Okay, so like right now that zoom is occurring, but this is a magnifying glass. We're inside that focal point. As we move this farther away, and it's going to be very hard to see. Let's see if we can see it. Let's move this far away. We notice more eyes on the other side of that. So we notice at some point we gotta get this blur, and that's because that's where there's no image being formed there. Okay, so that's what's kind of going on with these lenses. Because of this though, everything we learned about mirrors, we just apply it to these lenses instead. Everything about mirrors just gets applied to the lenses and we're fine. And this means that our mirror equation, which I was calling the mirror lens equation, applies the exact same. 1 over f equals 1 over di plus 1 over do. Nothing is changing there. The only thing that we have to be careful about is recognizing when we have positive and negative focal lengths. Negative focal lengths are for concave lenses, because just like the mirrors, we got to get a negative number. We got to get a negative distance out of that. You think about negative distances as where should the light be? A negative distance is where the light shouldn't be. So, if we're looking at this here, the light should be over here. This is the light path. The light path is not here. It's not on this side. It went through the lens and out. So this is a negative image distance. If we go to our case 6, we clearly see that the light is over here. The light path, that is. There's no light path over here. This is made up. This is going to have a negative image distance as well, because the light really shouldn't be interacting here. It's just what we see with our eyes. It's a phenomenon of being a human, okay? So that is the idea of thin lenses, both convex and concave. How we can relate them to the mirrors, which we already know really well, how we can use the mirror equation, how we can use our magnification equation, m equals either high over ho, which equals negative di over do, and everything still plays the exact same way. On just one final note, sometimes you'll see this, sometimes you won't, but when we look at the double convex, we showed how the light came through it, and it technically is bending once and then bending twice. For the double concave, it's technically bending twice as well. It's bending away and then bending away again, and we'll talk about why that is later. But sometimes for these perfect systems we have, we just like drawing these lenses a little bit easier. In this case, double convexes will just be a straight line up and down. That is a double convex lens. It is very, very thin. For a double concave lens, we'll draw it as a straight line with a little Y on the top and the bottom. Okay? So if you ever see these, they really just correspond to the type of lens that's going on there and what you're actually looking at. Okay? So nothing to it more than what we already know. We will talk about why these light paths change a little bit later. But in terms of the math and everything, like I said, everything's the complete same from what you already know for your mirrors. So take a look at some of the problems and get back to me on any questions you've got.